Right, so for part D, notice that it's a recursive function, right? Once we call helper, helper calls itself twice in each call, and then this is its base case, and this is its recursive case, okay? So whenever we have a recursive function, a really good thing to do to analyze its runtime is to draw a recursion tree. So because we only care about n in this case, we don't care about m, we can just say that our nodes are going to be in terms of n. So we start at n in the first level at level 0, and then this is going to call two recursive calls with n minus 1, right? And I got that from this line. And these are each going to call with n minus 2, and so on and so forth until we get down to 1, right? And there's going to be a lot of nodes annotated with 1 at the very bottom of this tree. And so we can apply a really helpful recursion formula. So I equals 0 to the height of this tree of the branching factor, okay, and I'm going to squeeze in branching factor like here, and then we're going to times it by the amount of work per node per level, okay? And so I think you can just get rid of the per level part because we're already, doing it by I, which is the level. But basically we can determine from this recursion tree that the height is going to be n, because we're going from n to n minus 1, then n minus 2, all the way down to 1, decrementing by 1 each time. And then the branching factor, which I'm going to abbreviate as BF, is going to be 2, which corresponds to the number of recursive calls we make for each node. And then the amount of work per node is basically coming from this recursive case. We don't really care about the base case because remember, we only care about n as it goes to infinity. And so there's going to be, so the fact that n is less than or equal to 1 is not really going to apply to our case. So we only care about the recursive case, but here's the caveat. The recursive case also includes the recursive call, but we don't really care about the recursive call, right? Because this is what we're analyzing separately inside the summation. And so the amount of work is just inside the recursive case, but outside of the recursive calls. Assume that we have taken care of the recursive calls. And so in this case, it's really just the number of iterations of this for loop. Notice that m is passed in as n over 2, and it always stays as n over 2, right? We don't really do anything to this m. So, and then we're timesing by 2 each iteration, which means that it's basically log n over 2 iterations total, which is log n. So our amount of work is really log n. But notice that n isn't always applicable to every level of our recursion tree, right? At the root, it is n, but its children has n minus 1, and their children have n minus 2. And so really, we have to account for which level the node is at, which is why I wanted to include the per level here, okay? All right, so if we put everything together, this is going to be I equals 0 to n minus 1. And I say n minus 1 because we have n total levels and we're indexing from 0. That's a really, very detailed stuff, but it's not really going to affect your work, affect your end result if you didn't account for that, if you just kept it as n. And then the branching factor is 2 to the I, and then the amount of work per node is going to be log n minus I. So this kind of seems scary, right? Like, how do I evaluate this? So in these cases, it's really good to actually put a simpler upper bound on what this formula is. So this is actually less than or equal to I equals 0 to n minus 1 of 2 to the I times just log n, right? Because notice that log n minus I, right, is always going to be less than or equal to log n. Okay, well, this is really great because log n doesn't depend on any I, right? So we can actually put it outside the summation. So we have log n times I equals 0 all the way to n minus 1 of 2 to the I. And now we know how to do this part, right? This is really just a geometric series. So this is going from 2 to the 0, and then 2 to the 1, 2 to the 2, all the way, and we're summing that up. And the summation formula for a finite geometric series is basically a1 times 1 minus r to the n over 1 minus r. So I guess we can actually plug it in. A1 is going to be 1 in this case, and then the r is going to be 2. That's what we multiply each term by, right, to get the next term. And so that's going to be 1 minus basically 2 to the n minus 1 over 1 minus 2, which is negative 1, which means that we can flip the sign in the numerator to get 2 to the n minus 1 minus 1, right? So this is really just log n times 2 to the n minus 1 minus 1, okay? And basically, we only care about significant terms. So if we actually expand this out, this is going to be log n times 2 to the n minus 1 minus, whoops, getting my parentheses mixed up, minus log n, right? Log n is a lot less significant than this first term, so we can just ignore this part, which means that our answer is this first term. But also notice that we have this kind of annoying n minus 1 in the exponent, right? N minus 1 is basically the same thing as n. So what we can do is replace this with n and then just have our answer be log n times 2 to the n. And that is our answer. And think about whether it's worst case or best case, right? In this case, we don't really have any code or any way for us to skip our recursive call or the for loop, right? To break out of the for loop early or to call the recursive function a fewer number of times. And so actually the runtime that we found here applies to both the best case and the worst case.